Hi, today we'll talk about addressing facilities that are complex and the safety issues that are evident in facilities like that and cathodic protection needs within such facilities. Topics we'll talk about include what kind of structures are in such facilities and what are the needs for grounding or bonding and what kind of problems exist from those conditions. There are hazards that result from this situation, and we'll talk about the hazards, and then finally we'll address how do you fix these. So the kinds of structures in complex facilities could include cathodically protected structures, of course, and that could be piping or tanks typically. There also will certainly be intentionally non-cathodically protected piping, or at least it might be bonded in, but your intention was not to tie it into the CP system. There's also electrical equipment, perhaps motor-operated valves, other electrical devices that could be on the CP system, or it might be off of the CP system. And then there's grounding for any type of electrical system in a facility. Also within facilities, you will find perhaps buildings for measurement or control. There will be lighting structures or communication towers. There probably will be insulating joints, and there might in some cases be other below-grade features such as pits or vaults. And we'll want to think about each of the factors that are brought up with these types of constructions. So the kinds of problems we could run into would be if structures are not referenced to each other or not referenced to ground, there could be safety issues that result. And if they are referenced to each other, they could create corrosion concerns because of dissimilar metals or tying an active cathodic protection system to another object that was not part of the CP calculations. Other problems we could run into would be electrical equipment that's not grounded. That's not typical, but perhaps because of cathodic protection problems, people may have taken an action that left the electrical equipment not grounded. Or the equipment normally is grounded, but then that affects cathodic protection, and CP personnel might not understand, well, how could you fix such a problem? Other issues would be insulated joints that do not have overvoltage protection, resulting in a possible arcing hazard. And all of this could be in a hazardous defined location, or portions of a facility may have hazardous locations. So the real hazards involved would be if there are unreferenced structures, that means that they have no relationship to each other. One metallic structure could have voltage on it, and the other structure may not. And if there's an insulation system or a lack of bonding, there could be a notable voltage difference between them. And obviously that could be a risk to personnel or to insulation systems such as coatings or insulators. Basically, the voltage is not being limited or controlled. So it could rise to some level, and at some point you'll either break down insulation and then there will be a flashover or an arc. But if they're not referenced, that's more likely a case where there's not a corrosion problem because they are not referenced in the first place. There's no bond established. And it's usually bonds that cause corrosion problems by tying two different structures together. So in summary, we definitely have a safety issue, but we haven't created a corrosion issue in this story. Other hazards would be if we now turn the tables and reference or bond structures together. Well, now they can't support a voltage difference. At least specifically, it won't support an AC voltage difference, but there is a reason why it still could be a lightning over voltage issue. And we can get into that later, but it relates to conductor lengths and a property called inductance. And if we do bond, we now could have interference between systems. Either we could create a galvanic corrosion cell, or we might be bonding an active CP system to another structure. So in summary, We now have a possible corrosion issue or an interference issue, but we probably have addressed the safety issue via the bonding. Now, another situation. If electrical equipment is grounded, well, if it's grounded, it will meet the grounding codes, and this does establish an AC fault current return path that's needed and described in the codes so that breakers can clear and the hazard is removed. However, from a CP standpoint, any motor or other electrical equipment that's grounded now ties a cathodically protected structure to ground. But you can't remove that ground because of the codes and the inherent safety issues. So the summary here is we're back to having a corrosion issue, but not a safety issue. And if we flip that scenario around to where the electrical equipment is not grounded, now we clearly will violate grounding codes. The National Electric Code in the US and codes elsewhere say the same thing, that ground is needed for the clearing of a fault. When we remove a ground, you are taking away the fault current return path, forcing fault current to flow through the soil back to the panel, and a breaker probably cannot sense that, and so it will not clear the fault. So while there's not a cathodic protection problem, this would be a very large safety issue and is not acceptable. If we have insulated joints in facilities and those are not protected, meaning no overvoltage protection across the joint, clearly those are subject to failure due to arcing and overvoltage concerns, either a puncture of the insulation or tracking and conductive products being deposited, say externally or through a puncture. That would be a problem for cathodic protection. Sometimes people think of leaving insulated joints not protected and leaving one structure unreferenced to the other as somehow beneficial because of the concept of saying, well, I don't want to have this electrical event on one section of piping appear on a different section of pipe. So they perceive it as a positive, but the problem could be ultimately if the voltage rises, you will establish an arc and you could fail insulation or cause a leak on the pipeline. There could definitely be significant effects. So again, a safety issue, but not a corrosion issue. So to talk about hazardous locations, some facilities will have portions or the entire facility classified by someone as a hazardous location. So the issue here would be that there could be an ignition issue. If there were sparks or heat in a hazardous area, it could ignite a flammable mixture. It's very common to have classifications for hazardous locations. So, for example, there are divisions or there could be zones depending on where you are in the world. In the US, for example, it might be a Division 1 or Division 2 classified area where that relates to basically the inherent risk of ignition. Whether it's common to have a source of gas that could ignite or if it's less common. So Div 1 would be a higher risk, Div 2 a lower risk, or a site could have an ordinary location, which is non-classified. There are compliance requirements for products and methods used in hazardous areas. For example, the National Electrical Code in the US or the Canadian Electrical Code in Canada describe the equipment and the methods allowable in a Div 2 or Div 1 area, and likewise for other zone classifications around the world. But it will affect how we accomplish overvoltage protection because we need to comply with the hazardous requirements. So now we'll take these principles, let's apply them to specific facility arrangements so that you can see how this is employed. We're going to look at several different cases. One would be just insulated joints. That's worthy of its own example. We'll look at piping that has not been referenced to ground or other piping. We'll look at electrical equipment on facilities. We'll look at grounding systems, fences, and finally, we'll take a look at power utility incoming service and how that might be addressed. Although this last example is a little bit involved for today's discussion, I'll just touch on the factors involved with power utilities. So first on insulated joints. there could be sections of a pipeline that have cathodic protection, and then someone might create a floating section in the center, say in a facility. And the thought might be that they have sensitive electronic equipment on that middle section, and they're afraid of it being harmed by electrical events. So they leave it electrically not bonded or grounded, and not referenced to the other structures. The concern is going to be voltage. Overvoltage could exist then across each insulated joint and from each section of piping relative to grounding systems or other structures in a facility. So we could have an overvoltage condition due to the floating section unreferenced to other sections or ground. The solution to this would be to provide overvoltage protection devices or decouplers across the insulated joints for their protection, and now we've addressed the arcing and the overvoltage concerns. We've referenced all sections of piping to each other via this method, and because the section in the center, in this example, is not cathodically protected, it can just be solidly bonded to grounding systems without an effect. In fact, this is advantageous because now the section in the center that contained our hypothetical measuring equipment or sensitive electronics has now been solidly referenced to a grounding system and actually may provide protection then for that electronics. In the case of facilities, like separate ownership of facilities and fences that separate those, here's an example of two different facilities without much detail shown that have grounding systems and have separation between them via fences. And we now need to consider what risks and solutions are available to us. Let's say that we own facility A and facility B is a foreign party, that we aren't in control of the details of their layout or site or design. The concerns would be that voltage could be established between either grounding system and the fence if there's no reference or bond. Let's say that our facility A does have an impressed current system on piping and the facility, but it also ends up being tied to the grounding system, either inadvertently or maybe by design. So the concern would be we don't know anything about the other facility, can't know how they operate or if they even have a cathodic protection system. We also don't know if they've bonded to the fence. So there are safety concerns, as well as our own inherent interest in preserving our CP system and not bonding to theirs and having that be an unacceptable reading. A solution, a proper solution, could be that a decoupler connects our cathodically protected facility and grounding system to the fence. So the fence now is not part of the cathodic protection system, receives no current, but yet a safety bond via the decoupler is established so that the fence and the grounding system will be at the same potential in an event. And then on the foreign system, I've taken some liberties. Let's say the proper procedure would be that they should bond their grounding system to the fence if they don't have CP, or if they do, they'd want to consider if they need a decoupling, and they might need supplemental CP if they do end up being directly bonded to a fence. And I've just proposed something, but it could be of any appropriate design. We may not be in control of facility B, but I'm just trying to show proper actions taken if one did have any influence on the situation. Let's switch to a discussion about tanks that may have electrical equipment on them. The typical tank may have driven ground rods around its periphery, perceived to be a lightning protection scheme. If the tank has cathodic protection, those grounds will play a part, but the site actually is a little bit more complex than this. Here in the next slide we show how there probably is electrical equipment on that tank as well. There could be pumps or motors or level gauges or lights, any such equipment on there that receives AC power. Therefore, that power comes from an electrical panel that ties it via a grounding system to the ground grid of the facility, and there could be other tanks or more to this site that's not being shown. We also will assume that clearly we have to have piping enter or exit that tank, and it may or may not have insulated joints. Let's say in this case that it does. Well, our cathodic protection system for this site, let's make it an impressed current system. When it's tied to the tank and its ground rods and there's electrical systems, the cathodic protection attempts to protect everything. In fact, preferentially, it probably will have current heavily go towards the ground rods and the grounding grid of the facility. And again, this facility may be much larger and have additional structures within it. So obviously detrimental to CP, or we just have to put out a massive amount of current in order to attempt to shift the structure. Now, further complicating this would be that it's common for tank sites to be classified hazardous locations depending on what material is in the tank. Let's say this is some type of petroleum facility. Very commonly, for an area around that tank, that will be a Division 1 location, or perhaps Zone 1 elsewhere, showing the highest classification. So any solutions employed have to be also rated for Div 1 if they're in that area. There could be a Div 2 area, perhaps the insulated joint that's over on the right could be classified as Div 2 unless it itself is within the Div 1 area that is created by proximity to the tank. Then itself it will be Div 1. And at some point further away, certainly by the point of reaching an electrical panel, that has to be an ordinary location because of the arcing nature of breakers and that type of construction. So we probably have all three types of classifications or situations in this story. So any solutions we have must comply. If we employ a decoupler in the ground, which is allowed per the National Electrical Code if it's a listed product or a certified device, if that were placed in series in the ground and conduit, now the electrical ground grid of the facility does not appear to the CP system. It is now trying to protect just the tank bottom. It will still protect the ground rods if they're directly bonded to the tank, but the CP current requirements probably have been cut down dramatically. If the decoupler is in the Div 1 area, it would be listed for that. Very commonly, it can be placed in an ordinary location or in a Div 2 location. And here, I show it on the ordinary location side of that imaginary line. Looking at a decoupler added to the right to protect the insulated joint, that could either be Div 2 or Div 1, appropriate for however that site is classified. But now the insulated joint has protection as well. Let's switch to a discussion about specific pieces of electrical equipment on a pipeline, and we'll use the example of a motor-operated valve. We alluded to this in the last example with a tank that had electrical equipment, and we'll just drill down a little deeper. So electrical equipment will have a grounding conductor for the sake of clearing faults and personnel safety. And that ground will run from the case, which is tied to the cathodic protection system in this case, to an electrical panel which ties to ground rods, and then further on it goes all the way back to the transformer and back to the utility. So cathodic protection systems can have an effect in trying to protect the grounding system as well, and that's detrimental to CP. So if that's detrimental, can we break that ground? Could it be removed in some way? Well, electrical grounding codes require it to be there. It really is not an option for removal. So even though it causes CP problems, it cannot be removed. However, there are certified or listed devices, specifically decouplers. If they are so listed, could be placed in series in the ground to block cathodic protection current, but meet all of the AC safety grounding codes. And here we show that installed. No CP current is flowing now to the grounding system of the facility or onward to the power utility or the rest of the world. Now another option that could have been employed is to place insulated joints on either side of the motor-operated valve, and now that small section containing the operator is not really part of the cathodically protected pipeline. Now if the facility was built this way, that's a practical choice. But if remediation of a site that does not have insulated joints is being considered, it's not very easy to take a pipeline out of service and then cut into the pipeline to place insulated joints in service. So a decoupler would be an easier approach, but in order to show all options, we depict here that insulated joints are a possibility. However, a complete installation would have protection for the insulated joints. Ideally, the protective device would be on each of the insulated joints. But I do show an option here where one is used and then a CP bond connects from one cross-country pipeline around the whole valve arrangement to the opposite side, which is a common arrangement for cross-country pipelines. Again, ideally, the other joint would have protection because even though this one protective device is technically in parallel with the other insulated joint, there is that effect of conductor length and an electrical property of inductance that for fast rising waveforms such as lightning can still cause a fairly large voltage drop in the conductor itself as lightning current flows, producing a large voltage drop across the far insulated joint, possibly to the point of not protecting it. There are more papers and articles on this inductance effect, and you might contact us if that is of interest. A final application that will just be briefly mentioned but not fully explored would be the power utility service that comes into a facility that has cathodic protection. Because utility systems are generally grounded and they will deliver power at a different voltage to a facility, and those facilities are all grounded, if that grounding of the facility ties into cathodic protection, whether intentionally or inadvertently, your cathodic protection also is trying to protect the utility copper grounding system, and which has a great negative effect on CP. The way it actually connects into the utility is shown in this diagram. The grounding conductors of electrical equipment or to buildings or bonds comes back to the grounding bus in the main disconnect. That ties into grounded neutrals, which tie to transformer cabinets or tanks, which tie to the utility grounded neutral, and then on to the rest of the world. So that's the path by which you have your problem in the first place. What is possible is decoupling to solve this problem at two locations. One could be employed by the power company at the transformer for the sake of the client. Another one could be done on the customer's facility, the secondary side, at the main disconnect panel, and that's worthy of another presentation. So if that is also of interest, please contact us. In short, bonding structures should be accomplished, or decoupling, if there's CP involved, should be done in order to eliminate overvoltage safety issues. Without that, we would have high voltage conditions for either insulation systems and have arcing and flashover, or we'd have hazards for personnel. And we also should isolate appropriately so that we can segment cathodic protection systems or not create galvanic corrosion cells by the safety bonding required. So both of these factors have to be considered together in order to address both issues. If there are additional questions, we can be reached for further contact at Dairyland. The website dairyland.com also has a lot of resources and material available. Thank you.